In the last lecture, we were looking at forced convection, specifically the flow past a flat plate. Okay. X is the streamwise direction, Z is the cross stream direction. You have some velocity profile, okay, and you have a heated section only for x greater than 0. Okay. You have a heated section only for x greater than 0. So, T is equal to T infinity far from the surface, T is equal to T wall at this heated section, and T is equal to T infinity before the fluid comes into contact with the heated section. Okay. And we were looking at this in the case where the Peclet number was large. Okay. So, the equation, okay, for the temperature field, we defined the scale temperature field as T star is equal to T minus T infinity by T wall minus T infinity. In this case, the equation became Vx partial T star by partial x is equal to alpha d square T star by partial z square. Okay. If we neglect diffusion in comparison to convection, then we just get that Vx, okay, partial T star by partial x is equal to 0. If we neglect diffusion in comparison to convection, then we just get Vx partial T by partial x is equal to 0. That means that the temperature is a constant throughout the domain. Okay. And for that, we cannot satisfy the boundary condition at the surface. Note that the boundary conditions are for at z is equal to 0, okay, T is equal to T w for x greater than 0, okay, and for z going to infinity, T is equal to T infinity, okay, and at x is equal to 0 at the start of the heating section, T is equal to T infinity for z greater than 0. Okay, that is, in the fluid the temperature is still T infinity because the heating has not yet started. Okay. So, if we just postulate that T is equal to partial T by partial x is equal to 0 throughout, right, then it basically tells you that the temperature is a constant throughout the domain. The temperature in the fluid in the heated section is the same as the temperature before the fluid contacted the heated section. Therefore, there is no effect of the wall on the temperature field in the fluid. So, that is the result that we get. Okay. And that is clearly not does not satisfy this boundary condition. Okay. That clearly does not satisfy the boundary condition that T is equal to T w at the wall. For that reason, we said that we have to postulate that there is a thin region of thickness delta, okay, of thickness delta, okay, within which there is a temperature disturbance due to the heating from the wall. As the fluid goes downstream, any heat that is generated at the surface, okay, that is transported perpendicular to the surface, is swept downstream due to the rapid convection, and therefore, the effect of heating is restricted to a thin region near the surface. Okay, so, that is the rationale. Okay. Okay. And the other assumption that we had made in this case is that at a downstream location x, okay, at a downstream location x, okay, at a downstream location x, the boundary layer thickness depends only upon x. Okay, delta depends only upon x at a downstream location x. It does not depend upon the total length L of the heated section. Okay, it does not depend upon the total length L of the heated section. It depends only upon x. So, the relevant length scale in the cross stream direction in this case is delta. Okay. The relevant length scale in the cross stream direction for scaling the z coordinate. Okay. For scaling the z coordinate, the relevant length scale in the cross stream direction is delta. Okay. And therefore, you scale z by delta, which is a function of x. okay, to get the scaled, okay, coordinate. Okay. And this scaled coordinate is a similarity variable because it contains both z and x. Okay. This scaled coordinate is a similarity variable because it contains both z and x. Okay. If you recall, when we did unsteady diffusion, okay, into an infinite medium, we had similarly defined a scaled coordinate. There it was z by root alpha t, okay, for an unsteady problem. In that case, we could get that just from dimensional analysis. In this case, we are getting the scaled coordinate from the condition that effectively in the z direction there is no length scale. The length scale itself is set by a balance between convection and diffusion, and that length scale is only a function of the downstream distance from the start of the heating section. Okay. So, that is the basis for this assumption in terms of a similarity variable. Now, once we have defined the similarity variable, we have to express the equation and the boundary conditions entirely in terms of this similarity variable. Okay. We have to express both the equations and the boundary conditions in terms of the similarity variable, and the similarity transform is valid only if both the equation and the boundary conditions can be expressed in terms of this similarity variable. Okay. The similarity transform is valid only if both the equations and the boundary conditions can be expressed in terms of this similarity variable. Okay. So, therefore, I write eta is equal to z by delta of x. Okay. And as I also said, close to the surface you can use a linear approximation for the velocity profile, because the velocity is 0 at the surface. Velocity has to increase linearly from the surface. Therefore, we can use a linear approximation for the velocity close to the surface as Vs prime times z, where Vs prime is equal to dVx by dz at the surface. Okay. So, we use a linear approximation for the profile. And then we have to express the temperature derivatives with respect to x and z in terms of the temperature derivative with respect to eta. Okay. And that we had done in the last lecture. Okay. Partial t star by partial z is equal to partial square t star is equal to 1 by delta Similarly, the second derivative, partial square is equal to 1 by delta square d square t star by d eta square. Okay. And partial t by partial x is equal to eta depends upon x only through the dependence of delta on x. Okay. So, I have to take the derivative of delta in the denominator with respect to x. Okay. So, I will get minus z by delta square d delta by dx, okay, which is minus eta by delta substitute that into the equation. Okay. Vs prime z partial t star by partial x is equal to alpha okay. Vs prime z is delta times eta, dt by dx is minus eta by delta okay, is equal to alpha by delta square d square t star by d eta square. we can collect terms that depend only upon eta and terms that are depend individually on delta and Vs prime. So, this is minus eta square dt star by d eta, okay, multiply throughout by delta square by alpha, right side will be d square t star by d eta square, okay. And on the left side I will have Vs prime delta square by alpha d delta by dx. Okay. Now, this can be reduced to a similarity equation only if this is a constant, okay. Only if this term here is a constant, only then can it be reduced to a similarity equation, okay, because if this is a constant, this depends only upon, the equation depends only upon eta, okay. So, we had done a calculation where, okay, in the last lecture, okay, Vs prime delta square by alpha d delta by dx is equal to some constant c delta, okay. And we had got solved this subject to the condition that delta is equal to 0 at x is equal to 0, okay. We had solved this subject to the condition that delta is equal to 0 at x is equal to 0, okay, to get delta is equal to 3 c delta alpha by Vs prime whole power 1 by 3. Okay. So, that is the condition under which the equation is dependent only upon the similarity variable and not individually upon z and x or individually upon delta and x. Okay. Okay. So, that is the condition under which the equation can be reduced to a similarity form. Okay. So, therefore, with this transformation the equation becomes c delta eta square dt star by d eta is equal to d square t star by d eta square. Okay. Now, we have to also satisfy the boundary conditions. Okay. The boundary conditions have to now be expressed in terms of eta. Okay. The boundary conditions have now to be expressed in terms of eta. Okay. Z is equal to 0 means that eta is equal to 0 because eta is equal to z by delta of x. Okay. T is equal to T w, okay. T star is equal to 1. Okay. At eta is equal to 0, T star is equal to 1. Z going to infinity means that eta going to infinity. Eta going to infinity, t is equal to t infinity. Note that t star is equal to t minus t infinity by t w minus t infinity. Okay. Note that t star is equal to t minus t infinity by t w minus t infinity. Therefore, t star is equal to 0. Okay. X is equal to 0. Okay. At x is equal to 0, delta is equal to 0. Okay. Note that eta is equal to z by delta. At x is equal to 0, the start of the heating section, the boundary layer thickness is 0. For z greater than 0, eta goes to infinity. Okay. If delta is equal to 0 and z is greater than 0, eta goes to infinity, t is equal to t infinity, which means that t star is equal to 0. Okay. So, these are the boundary conditions in terms of eta. Okay. So, these are the boundary conditions in terms of eta. Note that two of these reduce to the same condition. Okay. Two of these, the condition for z going to infinity and x is equal to 0, they both reduce to the same condition when expressed in terms of eta. That is expected because you should have only two boundary conditions in eta, whereas in the original coordinates x and z, you had a second order differential equation in z, which means two boundary conditions, first order in x, which means one boundary condition. Therefore, these reduce to just two conditions, one at eta equals 0, the other for eta going to infinity. Okay. So, the boundary conditions, okay, T star is equal to 1 at eta is equal to 0, T star is equal to 0 for eta going to infinity. Okay. So, this equation and these boundary conditions have now to be solved in order to obtain the temperature field in terms of eta. Okay, in order to obtain the temperature field in terms of eta. Okay. And then we have this expression for delta. Okay. So, we can express it back in terms of the original equations x and z using this expression for delta. Okay. My apologies here, I have missed out a factor of x in this. Okay. If you refer to the last equation, there is 3 c delta alpha x by V s prime power 1/3. Okay. Alpha is dimensions of length square per time, V s prime is 1 over time. Okay. So, you can see that this has dimensions of length. So, how do we solve this equation? We have to define dt star by d eta is equal to some new variable w. Therefore, I will get minus c delta eta square, okay, w is equal to dw by d eta. Okay. Therefore, w is equal to, okay, dividing throughout by w and multiplying by eta, we will get dw by w is equal to minus c delta eta square d eta log of w, okay, plus a constant, log of w is no constant here, log of w is equal to minus c delta eta cubed by 3 plus a constant a. Therefore, w, which is equal to dt star by d eta, is equal to e power some constant c, e power minus integral, okay, minus c delta eta cubed by 3, okay, with a constant c1, okay, where c1 is a constant of integration. Therefore, T star is equal to c1 integral 0 to eta d eta prime e power minus c eta prime cubed by 3, okay, plus c2, okay, where eta prime is the variable of integration. The variable eta is appearing in the upper limit of integration, okay, when you do this integration. Okay. Okay. Boundary condition, okay, at okay, eta is equal to 0, T star is equal to 1 implies that C2 equals 1, eta going to infinity T star is equal to 0 implies that C1 is equal to, okay, minus 1 by integral 0 to infinity d eta prime e power minus c delta eta prime cubed by 3. Therefore, the equation for the temperature field is T star is equal to 1 minus integral 0 to eta d eta prime e power minus c delta eta prime cubed by 3 by integral 0 to infinity that is the temperature field, that is the solution for the temperature field. Okay. This integral from 0 to infinity, okay, this integral from 0 to infinity can be written in terms of special functions. Okay. This integral from 0 to infinity can be written in terms of special functions. Okay. Integral 0 to infinity eta prime cubed by 3. Okay. This can be written in terms of special functions as gamma of 1 by 3 by 3 power 2/3 c delta power 1/3. Okay. Okay. So, with this T star is equal to 1 minus 3 power 2 by 3 Okay, so, this is the final equation for the temperature field in terms of eta. Okay. This is T minus T infinity by T wall minus T infinity. Okay. So, this is the final equation for the temperature field. Now, we can make an important point here with respect to we can make an important point here with respect to eta and z and x. Okay. Note that eta is equal to z by delta of x is equal to z by 3 c delta v s prime x by alpha whole power 1/3. Okay. And I have this integration over eta prime here. Okay. I have this integration over eta prime here. Okay. I can convert this integration into eta prime into another variable eta star. Okay. I can define eta star is equal to c delta power 1/3 eta prime. Okay. I can define eta star is equal to c delta power 1/3 eta prime. Okay. And then you can see that these two put together become just eta star. So, I will get T star T star is equal to 1 minus 3 power 2 by 3 by gamma of 1 by 3 integral 0 to c delta time eta prime cubed is eta star cubed. The variable of integration is d eta star, which is c delta times d eta prime. Okay. That means that the upper limit of integration has to be c delta power 1/3 times eta. Okay. The upper limit of integration has to be upper limit of integration here has to be c delta power 1/3 times eta, which will be z by 3 v s prime x by alpha whole power 1/3. Okay. Sorry, it should be alpha by v s prime. Okay. Interchange v s prime and alpha in the equations. So, this will be let us examine this equation a little bit. Okay. Let us examine this equation a little bit. Okay. You can see that this equation does not explicitly depend upon c delta. Okay. It does not explicitly depend upon c delta when expressed in terms of the original variables z and x. Okay. It does not explicitly depend upon C delta when expressed in terms of the original variables z and x. Okay. Note that C delta is a constant that we had imposed. Okay. The original equation did not contain this constant C delta. Okay. The original equation did not contain this constant C delta. Okay. C delta is a constant that we had imposed. Okay. Since the original equation did not contain C delta, the final solution in terms of the final x and z variables should also not contain the constant C delta. Intermediate solution in terms of eta of course can contain C delta. Okay. The equation for eta in terms of delta contains C delta, the temperature equation for T in terms of eta contains C delta, equation for eta in terms of delta the equation for delta in terms of x contains C delta. However, the equation for the temperature field in terms of x and z should not contain C delta, okay, because that is a intermediate constant that we had arbitrarily imposed. Okay, that is an intermediate constant that we had arbitrarily imposed. It was not a parameter in the original equation, right. Therefore, even though we have imposed a constant here in order to get a similarity solution, the temperature in terms of the similarity variable depends upon C delta, boundary layer thickness depends upon C delta, but the temperature in terms of the original variables x and z cannot depend upon C delta. Okay. And that is this solution for the temperature field. Okay. So, the temperature field in terms of x and z ultimately will not depend upon C delta. So, this is the temperature field that we have. Okay. It does not depend upon C delta. Therefore, in future we can consider that constant to be 1 without loss of generality. Okay. In general, we can consider that constant to be 1 without loss of generality. Okay. The flux Qz is equal to minus k partial T by partial Z into Tw minus T infinity, okay, partial T star by partial Z. Delta of x partial T star by partial eta. Okay. Just expressing in terms of scaled variables. Okay. The flux at the surface Qz at z is equal to 0 is equal to minus k into Tw minus T infinity by delta of x partial T star, or this should be a total derivative because we have used a similarity variable dt star by d eta at eta is equal to 0. And this dt star by d eta at eta equal to 0 is just equal to this constant C1. Okay. It is just equal to this constant C1. Okay. You recall that we had solved for dt star in terms of this constant C1, and C1 was given by this. Okay. Therefore, this is equal to minus k into Tw minus T infinity by delta of x into C1 was equal to 3 power 2 by 3 into C delta power 1/3 by gamma of 1/3. Okay. Expanding out delta, okay, expanding out delta 3 alpha Vs prime C delta by 3 alpha Vs prime x C delta by Vs prime whole power 1/3 into 3 power 2/3 C delta power 1/3 by gamma of 1/3. Okay. And this should have a negative sign here because C1 had a negative sign. Okay. So, if you recall, C1 here had a negative sign in front of it. Okay. And once again you will see that the C delta power 1/3 will cancel out. Okay. And I will get it as k into Tw minus T infinity by into 3 power 2/3 by gamma of 1/3 and here I have 3 alpha x by Vs prime power 1/3. This is the heat flux at a given location x. Okay. What is the average heat flux? Okay. The average heat flux I will continue in the next lecture. Okay. What is the average heat flux? I will continue that discussion in the next lecture. I will see you then.